Now the whole idea with bubble sort is if I ever look at a pair of two elements and they're out of order, you swap them. That's it. And you just keep doing that over and 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 over until it's sorted. Now, really, excuse me, and let me make sure I'm actually recording. Okay, good. So really, the order that I do those checks and swaps doesn't really matter at all. If I have two numbers and they're out of order, I just swap them. And let's quickly throw up so let's say I have all right, so here's my list. All I have to do is look at things that are adjacent, check if they're out of order. So, I don't know, let's look at the 2 and 7. Are they out of order?
True.
2 and 7 are out of order?
False.
False. Come on. 9 and 5, are they out of order?
Yep.
All right, so we can swap those. Is 5 and 2 out of order?
True.
Yeah, okay. Is this 5 and 7 out of order?
True.
Great, it's sorted now. Let's go back and do that again with a slightly different list. Now it's bigger. Okay. Someone tell me two that are out of order. Just yell.
8 and 2.
The what? The 8 and the 2. That's what I heard. Okay. Let's do 2, 8. Okay, now what? Anything else?
1 and 5.
1 and 5. Well, there is no 1 and a 5. We're only looking at adjacent things. They have to be right next to each other.
No, 1 and 7.
Oh, 1 and 7. Okay, yeah. 1, 7. Okay. What else? Anything else out of order?
8 and 6.
8 and 6. Yeah, you're right. Nope. 6, 8. There. Anything else?
4 and 1.
4 and 1. Oh, yeah, you're right. Anything else?
8 and 1.
8 and 1. Oh, yeah, okay. Anything else out of order?
5 and 2.
5 and 2. Yeah, okay. Anything else out of order? 5 and 1. You guys are always focused down here. Who cares about down here? Anything else out of order?
2 and 1.
2 and 1. All right, yeah. Anything else out of order?
7 and 4.
7 and 4. Oh, look at that. You're right. 4, 7. Anything else out of order?
8 and 4.
8 and 4. You're right. Anything else?
8 and 4.
Oh, look at that. Anything else?
5 and 4.
5 and 4. Oh, yeah. Anything else?
7 and 8.
7 and 8. You're right. 8. Yep. Anything else?
5 and 4.
5 and 4. Nope, this one here, right? Anything else?
6 and 8.
6 and 8. Yeah. What else?
7, 6.
Anything else?
No.
No.
There we go. Now, that strategy is great, but of course we were all over the place, right? It wasn't a very systematic approach. We were arbitrarily picking things that looked out of order and then we fixed it and whatnot. But the general idea of just keep looking at adjacent things. If they're out of order, put them in order. And just keep doing that until you're done. But we can do this in a much more systematic way. And the systematic way is, let's just undo it. Everything. is you start at the beginning. We're going to focus on the 5. The 5 and the 8. Are they out of order? This is an easy question. No, they're not out of order. Is 8 and 2 out of order?
Yes.
All right, so great. 2, 8. Is 8 and 4 out of order?
Yes.
Is 8 and 7 out of order?
Yes. True.
Oop. Is 8 and 1 out of order?
Yes.
Is 8 and 4 out of order?
True.
Is 8 and 8 out of order?
No.
No, all right. Is 8 and 6 out of order?
Yes.
Great. Is our list sorted?
No.
No. We're not quite there yet. But it's better. And interestingly enough, that element at the end, that 8, would that 8 go anywhere else? No. I mean, we could argue, well, there's 2 8s, so which one comes first, really? All right, fine. Let's for the sake of making things simple, let's turn that 8 into a 9 and pretend it was a 9 the whole time. Just because now there's no duplicate of the 8s there. Notice that the last element, after one pass, the last element is where it should be. Would you agree?
Yes.
Yeah. So let's do another pass. 2 and 5, are they out of order?
Yes.
5 and 4, are they out of order?
Yes.
5 and 7, are they out of order?
Yes.
Who said yes? Come on. 1 and 7.
Yes.
7 and 4.
Yes.
8. Whoop. 7 and 8.
No.
8 and 6.
Yes.
All right, so we'll switch them. There. Is the list sorted?
No.
No, but the second last element, after 2 passes, the second last element is where it belongs. Right? 8 is bigger than everything else, but less than 9. And it must be less than 9. It must be less than the thing that comes after it, because otherwise it would have been bubbled up the first time. Right? Otherwise, there would have been a comparison between the 8 and the 9. And 8 would have been bigger than 9 if it was bigger, but it's not. So after 2 passes, 2 things are guaranteed to be in the right spot. Let's do another pass. 2 and 4, are they out of order?
No.
4 and 5, are they out of order?
No.
5 and 1?
Yes.
Yeah. 4 and 5?
Yes.
5 and 7?
No.
7 and 6?
Yes.
Is it sorted?
No.
No, but the 7 is where it belongs now. And notice, I really don't need to compare the 7 and 8, right? Because, well, I already know 8 is where it belongs, so there's no need to keep going. Is it sorted?
No.
I think I already asked that. 2 and 4, are they in order?
Yes.
Ah, I tried to trick you. 4 and 1, do I swap
Yes.
them? All right, 1. 4 and 4, do I swap them?
No.
4 and 5, do I swap them?
No.
Oh, okay. Wait. Did I put 6 or 7 last time?
7.
Okay, 5 and 6, are they out of order? Do I swap them?
No.
No. All right, great, done. Is it sorted?
No.
But 6 is where it belongs. 5 is, but that's just dumb luck. I can't guarantee that. Is 2 and 1 out of order?
Yes.
Is 2 and 4 out of order?
No.
Is 4 and 4 out of order?
No.
Is 4 and 5 out of order?
No.
Okay, great. Am I sorted?
Yes.
Now, how did you check that it was sorted? You scan the list, right? You're like, yeah, okay, good, right? Yeah. So that's the idea of bubble sort. So instead of just arbitrarily swapping things, we're going to do it in a systematic way where you just keep doing these repeated passes. Now, the big question is, how much time does it take if I have a list of size n that I'm sorting? how how much work is it to do one pass? N minus 1. You're right, because I only have to compare. You're right, it's n minus 1. But remember, we're lazy, so we'll call it n.
Okay.
Right? We'll call it n. But you're right, because really, if I have n things, I only have to do n minus 1 comparisons. But the amount of work I have to do is like n. For one pass. But how many passes do I have to do in order to guarantee that it's sorted? I have to do one pass of a okay, I think I know what you're answering.
Oh, is that not the right question?
You answered a slightly different question correctly.
Okay.
But we'll come back to that one. Oh, I'm going to ask that question, and you're going to answer it. I'm going to reword it. If I ever do one pass and I don't swap anything, what do I know?
It's sorted.
It's sorted. That's what you're getting at, right? Yeah. So if I ever do a pass and nothing got swapped, well, if nothing was out of order, if nothing got swapped, that means nothing was out of order. And if nothing was out of order, then the list was sorted. Okay, great, cool. That's the best case scenario. So if I had a list like this, let's pretend this is the list I got. At the back, can you read these numbers at all reasonably? Yeah? Okay, cool. So, and someone else is like, yeah, great. If I can. Better? Yeah, okay. All right, I'm going to do bubble sort. Is 1 and 2 out of order? No. It's 2 and 4? 4 and 4? 4 and 5? 5 and 6? 6 and 7? 7 and 8? 8 and 9? All right, I did one pass. One pass took me like n work. But it just so happens if the list is already sorted, I only need to do one pass. That's kind of like that's the best case scenario. Let's try to reason about the alternative. Let's say I give you this list. Each pass takes n unit of work. So the question is, how many passes do I have to do? And let's see if we can find the pattern here. We'll do one pass. 9 and 8, are they out of order? Yes. 8, 9, you know what? I'm just going to do. After one whole pass, it'll look like this, right? 9 will have been bubbled up to the top. And now 9, the thing at the end, is where it belongs. Would you agree with that?
Yes.
Yes. So after one pass, one thing is where it belongs. After 2 passes, how many things will be where they belong?
2.
After n passes, how many things will be where they belong? N. You're right. So, the worst case scenario is n units of work. How many times? N times. But is it really n units of work every time? Do you have a question?
Well, what I was gonna say is that would it actually be n times? Because then when you get to the last 2, they just swap places in one go.
So I think what you're getting at is this, like,
Yeah.
after one pass, I go to the end. After the second pass, there's no need for me to compare. Like 8 will get here.
Yeah. Oh no, what I mean is like.
Oh, like it'd be like n minus 1 passes you mean, because the
Yeah.
things where it would belong. Yeah, I got you.
Okay.
Yeah, you're absolutely right. But remember, we're lazy computer scientists.
Okay.
You're thinking too hard. When 8 gets to here, there's no need to do this comparison. Because I know 9 is where it belongs. And then when 7 would get where it belongs, there's no need to compare. So every time I do a pass, I actually have to do one less comparison every time. But remember, how many, if I have a list of size n, on average, how many things am I going to have to look at in a scan for all scans? We talked about this 2 days ago, right? For every time I have to look at all n, I have to look at like none. For every time n minus 1, I have to look at 1. N minus 2, I have to look at 2. So what's the pattern there? On average, how many things do I have to look at? N divided by 2, yeah. So n divided by 2, we don't care about coefficients because that's just a linear scale. That linear scale doesn't really modify the n squared very much. The n squared part dominates the amount of work so much that we don't care about those coefficients. Now, let's try to visualize. Let's draw. All right, so this is 0, this is n, 0, n. The first time through the list, I have to do n minus 1 comparisons as you brought up, right? So we go 0 to n minus 1, right? Next time I do a pass, how many comparisons do I actually have to do? N minus 2, because there's no need to look at that last thing, because we know where it belongs. 0, 1, 2. Then how many things am I going to have to look at?
N minus 3.
Man, these markers. Maybe the red one? Ooh, that's good. Two, and then 1, right? So that's like how I can visualize the amount of work. Now, if this is n, and this is n, like this, is the part that's like, this is the work I'm doing. And this is the work I saved, right? What do you notice about this square? How much of the square is roughly filled out? Half of it. Oh, like half of n squared. Interesting. I'm not making a silly comparison. That's geometrically, yeah.
Is it half of n squared or is it n minus 1 factorial?
It's not factorial, no. Factorial is when you have multiplicative things. This is additive. Every time it's this work plus this work plus this work plus this work. And I'm glad you said that. So you had a question too? No, okay. Now, let's take a moment and think. So here I had one thing of work, two things. So really what I want to know is I want to know the total amount of work that's happening. And that's the sum of all these bars. We add them up together. Thank God we don't multiply them together. We add them together. So let's just add these numbers together. So if I have 1 plus 2 plus 3 plus n minus 2 plus n minus 1, right? And you know what? For easier math, I'm going to change this slightly. This really is for the easy math. Kind of ignoring those n cases, n minus 1 plus n minus 2. No, plus n. There'd be like an n minus 2, n minus 3, n minus 4, all between here, right? Now, who here recognizes that? I know you've all seen it before. I know, yes, you have. What are you saying? Someone was mumbling. Was it you? Well, take a guess. You could be wrong.
Summing up to n.
You're summing up to n. Correct. But what do we call that? Now this is what we call a series, right? But this is a specific type of series. What kind of series is this? An arithmetic series, you're right. Don't tell me you haven't seen this. I know you see it in high school, for crying out loud. If you don't, what's happening in high school now? Come on. I learned this in like grade 11. It's an arithmetic series. Does anyone remember the trick with arithmetic series? No. If you don't remember what it is, you probably don't remember the trick about it either. Have you ever seen an arithmetic series? Did anyone hear the story that goes with the trick? I think it's Euler. Let me just check. Gauss. Okay, it's Gauss. So there's a story. I'm going to assume it's not a true story. It very well could be. But there's a story. So there's a famous mathematician named Gauss. Raise your hand if you've ever heard of him. Raise your hand. Whoever, a Gaussian distribution, a normal distribution. Jesus, what are they teaching in high school now? Holy moly. Whatever. Famous mathematician named Gauss. And he was really bright. And what's typical of really smart students in school when they're like this big? Are they usually good students or annoying little shits? Annoying little shits, right? So Gauss is being an annoying little shit. So the teacher was like, well, I need to make busy work for him. So here, go add all the numbers up from 1 to 100, right? Busy work. And Gauss is like, all right. So he goes and he does it, and he comes back 2 seconds later with the result. And the teacher's like, what the hell? How the did you do this? That would take forever. 1 plus 2 is, okay, plus 3, plus 4. That's going to take a while. How did you do it so fast? She's like, well, it's easy. It's easy. All you have to do is you just take n, right? And then you do times n plus 1, and you just divide that by 2, right? That's all you have to do to get the sum. The teacher's like, well, how the hell do you do? Like, what? What? Why? He's like, well, it's easy. Look, watch. See, this is what you want, right? Of course, with Gauss, he had 1 to 100, but here we're looking at 1 to n. So let's see. So he's like, well, okay, look, I've got these numbers. 1 plus 2 plus 3, yada, 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 plus n minus 2 plus n minus 1 plus n. We want to add them all together, right? But here's what I'm going to do. I'm going to take that sequence, and I'm going to double it, right? So imagine that I wrote another, like, plus 1 plus 2 plus 3 plus 4 plus n, right? I just doubled the sequence. But we'll have to remember that we doubled it. Okay, so we got to remember we doubled. We did it 2 times. So we have to undo that later. So I've just doubled my sequence. As I'm telling the story, does anyone not remember? Like, does this ring a bell to anybody? You, I know you, because I showed you. One other person who rings a bell. So we do that, right? And then look. What's 1 plus n?
N plus 1.
It's n plus 1, right? You know what? I'm going to rewrite this series slightly differently. I'm not going to write it here. No. I'm going to write it like this. Plus n plus n minus 1 plus n minus 2 plus 2 plus 1. Right? So this is just that same sequence I had over here, but I rewrote it underneath it backwards. Right? Say yes.
Yes.
Awesome. So let's do that again. What's 1 plus n?
N plus 1.
Oh, that's just n plus 1. And then what's 2 plus n minus 1?
N plus 1.
Oh, it's just n plus 1. What's 3 plus n minus 2?
N plus 1.
Oh. And what's n minus 1 plus 2? You're going to have to do it one more time. And what's n plus 1?
N plus 1.
Is it n plus 1? Yes, it is. Great. So look at that. I mean, we're not done, right? I have to add all these numbers up. But all I did was add these two. And then I'm saying I'm going to add these two to that, and so on. So I'm not done. I still have a bunch of additions to do. But what's the funny thing about multiplication is just like do addition a bunch of times. So I have a whole bunch of n plus 1s here. How many do I have? As many as there are numbers in the list. Which we could say it's n, right? So it's just this right here is equal to n times n plus 1, right? That's all it is. Great, we're set. Oh, but we're not. Forgot something very important, right? I doubled the series by rewriting it for all those additions. So if I doubled something, I got to undo that double. So how do I undo a double? Divide it by 2. Oh, it's the same. Then, if I'm a computer scientist that was adding up all that work now, so now story time's over. If I'm the computer scientist adding up all that work, I go like, well, you know, this is a coefficient, right? Where did I put that eraser? This is a coefficient. You know, I can multiply that out. So that's really, you know, it's n squared plus n. Right? But I don't care about coefficients. Coefficients, they're useless. They just scale. And which of these two things grows faster than the other? N squared grows a hell of a lot faster. N grows linearly. This grows quadratically. Much faster curve, right? So if I'm a computer scientist, I want to be like, well, how much work is this taking? I mean, I could be more precise and be like, well, you know, it's like this. But computer scientists are lazy. We're going to be like, well, I don't care about a coefficient. And this extra linear amount of work we have to do is bullshit in comparison to this. So, or it's, you know, it's like n squared amount of work. That's what we're going to do. And just to impress, whoa, what is, let's say n is a 1,000. 1,000 squared plus 1,000. Right? So the 1,000 squared, this is the total amount of work that would be done if I cared about the linear part. Like, look, what is, let's add a couple more zeros. As n continues to grow, that linear part, it's bullshit. It doesn't matter at all. It has like no real effect on the total amount of work happening. Let's add a couple more zeros. Suddenly, Google's just like, it doesn't, whatever, times 10 to the 16. That little bit accounts for so little. Even if we go back to 1,000, right? What proportion of all of that? So 0.0999% of the total amount of work when n is 1,000 is from the linear part, from this part. That's why we don't give a crap about the linear bit compared to the quadratic bit. You know, if something grew, if we had an expression that said like n to the power of 3, we don't care about n squared anymore because n squared is going to grow so little compared. But that's just a little bit of complexity analysis, a little bit of analysis of how much work is our algorithm actually doing. So we saw 3 sorts. We saw selection, which is when we go through the list to find the current smallest element and append it to the end of our sorted list. And we just do that over and over and over. We go through and select the smallest that's left and then append it to the list. Then we saw insertion, which was take the thing off the top of the unsorted and find where in the sorted it belongs. We insert it where it belongs. And then last we had bubble. Bubble was flip that. And we saw that selection was actually kind of the worst of them all because it was always n squared amount of work. But we saw with insertion we could get lucky. Right? Remember if we got lucky if the data was reversed order, it would actually only be linear time. And we also saw with bubble sort, if we get the data and it's already sorted, we only actually ever have to do one pass on the data. Because if we ever do one pass and see that nothing changed, we're done. But there was that worst case scenario where if we had it in the reverse order, we would have to do n passes, each of which takes like n time, so n squared. So there's a huge difference between the best and worst case scenario. But bubble and insertion, we might get a little luckier, a little bit less work. But the truth is, those sorting algorithms suck. These sorting algorithms, I say they suck, but what's good about them is they're intuitive. Like we said yesterday, now that we've talked about them all, raise your hand if you've sorted something at any time in your life with some mishmash of these algorithms before. Of course you have, because they're intuitive. But the truth is, there's better ones out there, but they're not. I don't want to say the better ones aren't intuitive, but they're not as obvious. It's kind of funny. You might think, sorting. Like, how's James talking about sorting? Sorting. People have been sorting shit for millennia, right? He's talking about it as this great, interesting problem. Well, the reality is, humans have been sorting things poorly for millennia, and it wasn't until relatively recently in our history where someone was like, wait a minute, we can do this better. And it was because computer science is still a relatively new field, right? It was invented like 100-ish years ago, let's say. Not even really. And it wasn't until it was invented that people came up with the mathematics and the tools that they needed to start thinking and reasoning about these things. So until they had them, they couldn't really express and discover and prove why one algorithm might be better than another. One process of sorting might be better than that process, or vice versa. So sorting is interesting because 1, it's a non-trivial problem, but 2, you've all done it. 3, humans have been doing it for millennia. 4, we only recently figured out how terrible we were at it. That's what makes it so interesting. Is you think, sorting, that's a solved problem. Well, I got bad news for you. If it is, tell me the good sorting algorithm. So let's talk about 2 of the good sorting algorithms. I say good. They're relatively better, but there's pros and cons to each as well. Both of these algorithms require you to agree with me on one key core concept. All right? The key core concept is a list that is empty or a list that has one thing in it is sorted. Let's go with that as the premise. And I think it's a fair thing. If I give you a list with nothing in it and I ask you, is anything out of order in there? You would say, no, it's fine. If I give you a list with one thing in it and I ask you, is anything out of order? You would say, no, it's fine. It's sorted. Everything in that list is in order. Right? So a list that is empty and a list of size 1 is sorted. Okay. Does anyone have any questions about that fact? That fact is just, we can't even reason about that fact because it's like it's like a fundamental truth in the universe. Is all the elements on this table in order? You go like, yeah, there's only one thing. I mean, just nothing is out of order. Okay. So with that key idea, we can start to unlock two other interesting sorting algorithms. The first one I'm going to talk about is merge sort. Okay? So merge sort works like this. If I have two sorted lists, all right, it's really easy to merge two sorted lists into a bigger sorted list. Here's how you do it. And I'm going to explain it, but I'm willing to bet you could reason about this pretty easily yourself. I start with my one finger on the top, one finger on the bottom. And I ask, 1 and 1, which number is smaller? You know what, for ease here, let's make that a 2. So I'm going to build a new list based on these two sorted lists. The lists have to be sorted. I'm looking at 1 and 2. Which comes first?
1.
Perfect. So I add the 1, and now I'm pointing at the 4 and the 2. I move the index on the top one down 1. Because I took the 1 out. And I ask, what comes first, 2 or 4?
2.
Okay, great. So I'll go there. So now I'm comparing the 4 and the 3. What comes first?
3.
Now I'm comparing the 7 and the 6. What comes first? I'm comparing the 4 and the 4. What comes
Doesn't matter.
let's make this a 5, because the duplicates make it less fun. Now I'm comparing the 4 and the 5. 4 comes first. The reason I knew something was wrong is your face was just like, what? Okay, great. Now I'm comparing the 4 and the 5. The 7 and the 5. What comes first?
5.
Now I'm comparing the the 7 and the 6. 6. Then I'm comparing the 7. Well, actually, I don't need to compare anymore. The first list is done. I know that the 9 and 7 must just come next. Or 7 and 9. Right? That is the merge algorithm. You compare the two things and you take the smaller one and move to the next in the respective list. How much work did that take? Let's say I had two lists of roughly size n. 2n. But I don't care about coefficients, right? So computer scientists would say, it's n. It's n amount of work. All right. Yes?
In the case where 9 and 7 are reversed, would you do, because you'd be left with only one list with 2 elements.
You mean the 9 and 7 were reversed here?
Yeah.
So that would never happen because the lists have to be sorted.
Oh, okay.
Right? That was, I messed that one up.
Okay, gotcha.
So the lists have to be sorted.
Yeah.
So now with these, this is merge sort. With these two ideas, one, an empty list or a list of size 1 is sorted. And merging two sorted lists takes linear time. It's easy. With that, we have a way faster sorting algorithm. Here's how we do it. Let's start with the numbers 1 What numbers am I missing? 6, 5, 1, 2.
You have 5 already.
I have 5 already. I think I'm all set here. I'm sorting these numbers. Here's what we're going to do. We're going to start by pretending.
You're missing. Okay.
I'm just going to go with this. Let's start by pretending each of these numbers, they're not in a big list. No. They're in lists of size 1. Right? I'm going to take the first 2 lists and I'm going to merge them. 3 and 5, what comes first?
3.
Then 5 obviously comes after. Great. Now I'm going to do. Oh, this is actually really boring. Let me. What was the other number? Shoot, 4. 7, 4. We'll make this a 2 and a 1. Ignore the fact that I'm tweaking the problem to be more interesting. So now I'm going to merge the next 2. The 7 and the 4. What comes first? 4. Okay, great. And then just 7 tacked onto the end. Now I'm comparing 8 and 9. What comes first? 8. All right. And then, 9 gets tacked onto the end. And then 2 and 1. What comes first?
1.
Okay, great. I had to do 1, 2, 3, 4. To get to here, I did 4 merges. Now let's just merge the next 2 lists. 3 and 4, what comes first?
3.
5 and 4, what comes first?
4.
5 and 7, what comes first?
5.
Then 7 gets tacked on. 8 and 1, what comes first? 9 and 1, what comes first? No. 8 and 2, what comes first?
2.
And we just tack on the 8 and the 9. Great. So now I had to do 2 merges here. Okay, now 1 and 3, what comes first?
1.
3 and 2, what comes first?
2.
3 and 8, what comes first?
3.
4 and 8.
4.
5 and 8.
5.
7 and 8.
7.
Oh, we could just tack on the 8 and 9 at the end. Boom, the list is now sorted. I had to do 2 merges.
Go to 6.
No, that was 1 merge. And what was it? What was it supposed to be, a 7? There. So that's merge sort. But so here I did 4 merges, but here's the thing. How many things were in this list?
8.
8. And I did 4 merges, but it was 4 merges of 2 things. The next time I did 2 merges of 4 things. So, I mean, the total amount of work on each row was that. Right? If I had to do 8 merges, or if I had to do 4 merges, each one was 2, 8 work total. If I do 2 merges 4 times, if I merge 4 things 2 times, 2 things, each having 4 in there, every time there's 8 units of work on each row. So how many times do I have to do 8 units of work? Did I have to do it n times? How many do I have? I have 4 rows. I mean, really, I have like 3 rows because the last row is the result. That's a hell of a lot. That's pretty far away from n, right? In fact, imagine. I'm gonna ask. Here's a quiz for you. Imagine that I gave you an input size of 16, right? How many more rows would I have here if I actually had 16?
1.
Only one, right? Because I would do, the last one is 1 merge, then 2, then 4. If I had 16, I would have to do 8 merges of 2 things. Right? And if I doubled it again, well, I would have to do only 1 more row. I would have to do 16 merges of 2 things. So every time I double the size of the input, I only have to do one unit more of work. Does anyone know what this relationship is?
Like a square root.
Not square root, but your mind in the right place.
Like n over n? No.
No?
1 over
1 over n. You're all thinking in the right place.
You have to do n minus 1 merges?
N minus 1 merges? No, that's not where we're going here. The trick is, as I double the input, maybe I can reverse it. How can I word this in a slightly different way? If I double the input, I only have to do 1 more unit of work. Let me put it this way. Every time I go from one level to the next level, I'm halving the amount of work left. It's the same idea as that binary search, right? Every time I make a decision, I'm eliminating half of the stuff. So, who can think of what is the special mathematical operator we use to describe? So we have exponents, which is multiple multiplications. But what do we use when we have multiple divisions?
Isn't it a log function?
It is a log. Now, it's a log based 2, because it's always dividing by 2 every time. But the number of rows here grows at a rate of log base 2 of whatever n is. I have to do, each row requires n units of work, but I only have log base 2 of n rows on the order of that many rows. So this is way better. It's not n squared. It's n times log base 2 of n. And that is way better than n squared. Let's plot n squared and n times log base 2 of n. I don't know if it'll work properly here. Let's go to like alpha. No, maybe I'll just do it with actions. All right, well, this is not going the way I want it to, but I can show you a nice plot another time about how much faster one grows compared to the other. All right, we'll end here. See y'all later.